Welcome to day 2 of the forum. I think people are trickling in. It seems a lot quieter today than it was yesterday. I hope it stays that way. We are going to kick off this morning with a plenary talk. Charlie Zhang, no stranger to UCSD. He will be speaking. Sujit is going to be joining us shortly, but in the interest of time, I wanted us to welcome Charlie to the stage.
Thank you, Ramesh. Very happy to be back here in person, and it's really an honor to share our view from Samsung's side for beyond 5G and 6G. So as you know, Samsung is really involved in a very broad set of areas when it comes to consumer electronics business, right? But wireless technology, telecom is always very fundamental and important for us. That's why we really appreciate the partnership with UCSD and CWC over the years. Starting from the 5G days, the professors here did many very important and pioneering work, ranging from the device side for the RFIC, for the low power PA, and phase array, and also all these very important innovations in the system side as well. So really appreciate all the contributions. Your contribution is really important, as we collectively built 5G as we know today. I hope that as we embark on this journey toward 6G, we can repeat the success once again. So yesterday, we heard many different views about 5G, and some of the some of the criticism as well, right? So in terms of the technology not really living up to the expectation or initial vision that's being laid out 10 years ago, especially in the areas such as low latency and massive IoT. Some of it is really true, right? We all understand that. I think work is still ongoing to further optimize. But on the other side, I want to show you a different report card. If you look at this from a business side, from a commercialization side, I would say 5G is going pretty well. Right? So looking at the number of countries, number of operators that's rolling out their 5G services in different parts of the world, and especially some of the key numbers, if you look at, by prediction, or maybe it already happened, in year 2022, 3 years after initial 5G commercialization, we are reaching 1 billion users. That's actually half of the time it took for, compared to what we had for 4G days. It took 6 years to reach 1 billion users. So that's kind of another perspective, right? Definitely there's areas for improvement, but overall 5G is very timely technology and satisfies the unmet need for our consumers. So, what's going on in industry? You probably already heard a lot yesterday from the excellent talks. But if I were to summarize, right, what's happening, especially in the standard world, is we are doing something called 5G Advanced. We finished initial batch of the releases, release 15 to 17, sort of this initial build the basic framework for 5G. Now we are trying to do two things, really. One is to further improve the 5G standard based on the feedback and lessons we learned from the field. There are many. For example, the coverage is not as good as we had hoped, especially for millimeter wave band, but also for lower bands as well. Okay, not only for millimeter wave band. Even if you look at C-band, some of the coverage issues is there, and we need some good, we are developing good solutions to handle that. And another thing is, for example, in 4G days, the system, for LTE was designed in a very rigid way. Everything is really hardwired. But so in 5G, we are trying to correct that problem by adding a lot of flexibility in how we design the network, design the system, numerology, protocol, and everything. But we created the opposite problem, too much flexibility, which added a lot of burden in terms of how we can manage and operate. So that's another thing we are aware now. We're trying to address that. So of course, that's naturally happening, all the enhancement and the optimization for 5G. In the meantime, we also see, as we look forward to 6G, right, what are the motivating use cases? So we have quite a few interesting things on the horizon, including the truly immersive XR, including the mobile hologram and digital twin. All these are very exciting use cases in the future. Right? I mean, it requires technology advancements in many different areas, not only wireless communication. But then you look at requirements for these use cases, probably what we have today cannot really satisfy in terms of a capacity, throughput, and latency. So then, of course, naturally you will ask, what is 6G? I don't have an answer. But what we can talk about is what are the possible attributes of 6G, right? Knowing what we know today, knowing what everybody is looking at, and knowing some of the underlying trends in the technology landscape, right? Definitely we'll be looking for extreme performance. That's a given, both in terms of capacity, data rate, and coverage, solving some of the basic problems. But we're also talking about softwareization. We're talking about making things more trustworthy, security aspects, AI being a native part of it, and so on. The list is pretty long. Okay. So, which brings me to the next slide is talking about what we see are the key enabling technologies going forward when we go to 6G. Right? So you can see, 6G will, from a holistic telecommunication network perspective, it's more than radio technology, even though I'm gonna focus more on the radio side, the spectrum side. There's many different things you need to do, radio, UE side, the base station, and the core network and the cloud, right? So different aspects need to be addressed. A lot of exciting opportunities for innovation here. So I'm not gonna read through the list. You can read them later. Hopefully the slides will be available. Please feel free to take a look. One of the things I want to share today and I come across is, as you'll see later, I want to bring a lot of these, what we think are technical challenges to all of you, the professors and graduate students. So hopefully you can help us address them as well. Okay. Unlike what we did in the past when I give a talk here, I always talk about what we did. But now I want to change a little bit. I want to talk about what we think is important and interesting so everybody can contribute. So, but still, maybe next few slides, also I will share a little bit on what we are doing in a few select areas, including MIMO, including the new spectrum for upper midband, and including the terahertz, right? Including AI work and joint communication and sensing. But that's because of limitation of time. There's many other very important areas. For example, you'll hear later today on this reconfigurable intelligence service, and other topics. Energy saving, we heard yesterday, for example. I just don't have time to cover all of them. So we'll share some of these, what we are doing today. So starting from spectrum, right? Most important thing when we do wireless is always we start from spectrum. Where are the new opportunities? Have we used our existing spectrum in the best way we can? So our view is very simple. 5G, we have a two spectrum sort of strategy, right? We starting from what we had in 4G, we went into both C-band as well as millimeter wave. Similarly, for 6G, we think we'll again take a two spectrum strategy going forward. One is what we call upper midband. Some people call FR3 now. It's nicely situated between 10 gigahertz and 24 gigahertz, between our old friends, C-band and millimeter wave. Both of them we are quite familiar with, and then we are looking at on the other side of the spectrum, going beyond the reach of a millimeter wave band, going to some place where we call sub-terahertz. Okay, and they're targeting different use cases, really. As you can imagine, right, the lower band, the C-band or upper mid-band, the path loss is a little bit more favorable, so it's suitable to provide the wide area, nationwide coverage and capacity, whereas a higher end of a spectrum, then coverage is a little bit smaller, but it's really good for hotspots for use cases such as backhauling or front hauling or FWA. Okay. So first thing, what we call X-MIMO. This is targeting the extreme. It means extreme MIMO targeting the upper mid-band. So here you can see the fundamental question we want to ask ourselves is, can we utilize this new band, especially between 10 to 24, to achieve two things? Same coverage as C-band 3.5, but much higher capacity. Okay. If we can do that, then we achieved our goal. Okay, so that's really the fundamental challenge, and we pose for ourselves and also for all of you here. And then from there, we are looking at what are the technical challenges, what are the things that we have today, and what are the new things that we need to overcome, or new challenges we need to overcome. So definitely, the good thing is, since C-band and also the millimeter wave band, we already have good technology to tackle both of them, right? So we're not starting from scratch. So we definitely learn from all the lessons for both bands and trying to put them together, achieve this goal here for capacity and coverage. So we did very initial simulation. By the way, this is by no means comprehensive or conclusive, but we do see some hope. Right? In a single user simulation, on the left side, this is a plot for SINR for the to look at how the received signal could be if you are given a lot of antennas. In an ideal situation. The reason we are doing that, we want to make sure that we can do multi-layer. In this case, in this simulation, eventually we're targeting 8-layer communication for single user. Can we support higher order modulation or not? And on the right-hand side, that's more for multi-user. That's more targeting capacity. So both are important. Single user is very important for operators. They want to make sure that they, for the new generation of technology, you can improve the peak rate for a given user, which is very directly related to the experience of that user. Whereas on the other side, multi-user experience is related to the overall system capacity. And on that side, you can see also there's a potential, if we do things right, that we can really improve beyond the capability of C-band today, mostly because the nature of the upper mid-band means the wavelength is smaller, so we can pack much more dense antenna array in a similar form factor. So with that, you have more dimensions in the signal space to play with. So as you see here, right, as you try to load more layers of users, your performance don't saturate as quickly as what happens in the C-band. This is another sort of aspect. I just want to show everybody here, maybe give you a taste of how we look at things from industry perspective. Here, as I stated, right, we want to make sure coverage is the same. So how do we make sure about that? So what we do is we do these link budget analysis. It's a pretty standard way of doing things in industry. Then we look at what are the assumptions that's necessary to make the numbers work for both downlink and uplink. You can see the number of antennas that's necessary is a lot, in the order of several thousand antennas. Compared to what we see today, it's probably in the orders tens or maybe hundreds. Right? But with that, there's a chance, there's a hope that we can get there. Okay. And as I promised, this is a list of technical challenges we see. It's not limited to the system side, but it's also on the RF and device side. Because of all this huge number of antennas we have to pack there, right? The efficiency has to be very high, has to be more integrated. So you have to put more channels in a single chip in order to support 2,000 antennas. Right? And in the meantime, similarly on the digital baseband side, there's a lot of challenges associated with this huge dimension that's expected. Right? Even today, I would say in C-band, if you want to support 64 digital channels, that's heck of a work. You have to really put in specialized SoCs there to make it work. Now we are talking about going beyond that and go to 128 or 256 channels. The sheer number of digital signal come in can really overwhelm you. That's an area we see a lot of potential for good research contributions. How did you manage this complexity that's expected going forward? I mean, I was very happy to see yesterday, actually, there's one poster from a student talking about cell-free MIMO. I mean, that's another direction we are thinking about, because one way is to continue the traditional way, making things centralized. But at some point, it becomes less scalable. You know, once we're talking about we have to pack thousands of antennas there, right? And the form factor eventually will grow bigger, and you will run out of the tower space to put them. Okay, power consumption, especially front haul capacity, will really become a bottleneck. So instead of doing that, another way is going around that, maybe by distributing all the antennas around. Then you can limit all these, the problems, impacts from these bottlenecks, especially front haul capacity. I cannot emphasize enough going forward. That will be a big problem for us. Okay. So another benefit of doing this is eventually you see this future of maybe more universal coverage. The quality of this different user experience can be more uniform. Doesn't matter where you are. I mean, the concept of cell eventually can go away. It's more of a user-centric design in the future. The user enter a system can figure out the presence of this person or this user and figure out the best strategy, best subset of antennas to serve him. That will be the long-term vision of how things will evolve going forward. Okay, so of course it's not limited to the upper mid-band, the new band. It's also applicable to the existing band as well, but I see more of a need to innovate down the road, especially as we add more and more complexity to our design. So that's just the upper mid-band, right? As I mentioned, there's one part of the story. The other part will be the even higher frequency we are looking into, expanding into. I mean, I know there's a lot of concern about the current situation for millimeter wave rollout. I mean, it's a little bit slower than we expected, and then maybe a lot of people question why we need to look into this even higher frequency. To me, the answer is simple. We have to start from somewhere, and the spectrum is there. Between 92 to 300, there's 200 gigahertz of good spectrum out there that's not being used today. At some point, we will need to go there and find available spectrum. And of course, technology-wise, it's a lot of challenges ahead of us, I mean, as we listed here. Okay. So that's why we started a few years ago, initially working with UCSB, and they kindly provided initial RFIC, and now we have our own version. I just want to quickly share with you a few experiments. This is indoor test. It's pushing for throughput, the peak rate. You can see 30 meters, about 18 gigabit per second. And also then we did the outdoor test. That's longer range, a little bit lower data rate, right? So this is, by the way, outside of our Plano, Texas office. If any of you have a chance to visit us, please feel free to stop by. We'd be happy to show you our equipment and work in this area. Okay. So now quickly moving on. So one more topic, maybe in the interest of time, I want to kind of touch upon is AI. AI is already there. It's a lot of use cases already happening today, both on the network side as well as on the terminal smartphone side, right? So you can see today the difference between what we are doing today and what we are doing in the future for 6G is today it's more about separately optimizing the operations on the network side or on the terminal side. For example, network side, a lot of good work to replace these labor-intensive, tedious work to do the anomaly detection, to do root cause analysis, to optimize RF parameters. And on the smartphone side, there's a lot of good application that's coming up in the last few years. For example, if you watched Galaxy Unpack this year or maybe late last year, one of the features they mentioned is Wi-Fi optimization, Wi-Fi RF parameter optimization that can save you 10%, actually to be exact, 13% of power if you are streaming video. That's 13% of overall power for the whole phone. That's a huge number. That's what our team in Plano did. So we used the AI and machine learning to figure out, based on what's going on and user is doing at the moment, what's the best strategy to tune some of the parameters, controlling the duty cycle and wake-up time for that terminals. So that's already happening. But going forward, the difference will be in 6G, we can really build AI more natively as a part of protocol stack in physical layer, in RF and MAC layer and above. So really to achieve this end-to-end, more holistic optimization. Okay, so I see Joyce is giving me the reminder, 3 minutes left. So as I promised again, a whole list of questions and problems that we see are important when it comes to the system design. Okay, so hopefully we can share that later. So it cut across all these different aspects and the different layers of protocol stack. So one example maybe I can quickly share is what we did for AI-based nonlinear compensation. I think yesterday Bhaskar's talk actually gave a very good introduction for this, right? Bhaskar nicely summarized in a very simple way. AI is really good to deal with nonlinear systems, right? So in his case, he's looking at how to deal with 1-bit ADC, and in our case, we are using this and trying to deal with this clipping issue he also mentioned yesterday, right? As we all know, today there's a nonlinear region and there's linear region for the PA, right? So Peter is here, I know. But the problem is, if you're working on the nonlinear region, too much impairment. So that's why typically we back off the power. So we're not transmitting at the full capacity. The idea is very simple. Can we increase the power, but use AI at receiver side to improve the performance? And with that, you can improve the coverage, you can improve the throughput, both. Okay? So that's what we did, and some experiment we want to show you here. This is a conventional way. With this, you can achieve 13-meter coverage for a given constellation, but with this AI-based method, you can literally double it because you are transmitting at higher power. Okay, so out of time, so let me skip these joint communication sensing. I think it's really important and transformative technology, but hopefully in the future we have more chance to share what we are thinking about. And this is a timeline. As you see, it involves both ITU and 3GPP to work together to really make it happen. Another quick maybe point is, if you look at what's happening, the time for us to prepare fundamental 6G technology is not that long. You'll see 3GPP will start pretty soon. Okay. And with this, I'll conclude my talk. Thank you very much. And some resources in terms of white papers we have published in the 6G and spectrum area. Thank you.
Do you see I don't know what you call it, a value, a use, a need, a dependency for something that is mesh networking or mesh-like, particularly at the edge and amongst UEs to, especially for enabling that when you start getting into them sub-terahertz bands and all that, is that, do those things go hand in hand, or, is it a, is there not a kind of equitable way of doing it, which I guess is more of a business question versus a technological one? But just kind of your thoughts on that and how enabling or disabling it may be.
That's an excellent question. I think mesh is definitely a very important component technology. In fact, as a new topology, it's already being studied inside of 3GPP as part of so-called IAB, integrated access and backhaul, to improve the coverage and push the signal out further. So definitely, this is more complementary to what I was talking about earlier. Okay. If you imagine, if you distribute all the antennas out there, right, how did you provide backhaul to them? How did you send the signal to all these antennas? I mean, mesh could be one way of doing that. Okay.
All right, interesting. Thank you.
Okay. You're welcome.
One more question. All right. Dylan Kelly with Murata. I'm just curious, if you think about all the user hours on the network, what percentage of time is going to be in this 4096 QAM mode? Does it ever get used?
We don't have 4K mode yet. But the thing is, when you think about this system design, especially if I'm sitting, I mean, it's a really good question. I think you're right. The chance for you to use very high order modulation from a given user perspective is not a lot, maybe 10% of time, 20% of time. But on the other side, if you look at the network perspective, any transmission opportunity you save can be helpful for some other guy.
Yeah.
So overall, that's why we always push for higher throughput and trying to send something over as soon as possible. So you can save the bandwidth for somebody else.
I would just caution, the amount of man hours in the industry for the RF people like us to create components that will do 4096 versus 256. I mean, it is a huge hurdle for a 30% increase in spectral efficiency that may never get used. So please consider.
Yeah, sure. I mean, that's part of the reason maybe
Charge more for it.
with AI, you may be able to live with a little bit less strict RF requirement down the road in terms of EVM.
My dream would be to see a PDF of usage, by modulation order of the system.
Most of it is QPSK.
Yes. Thank you.
Okay, thank you.
The AI and the doubling of the range was very interesting. To double the range, you need 6 dB more, as you know. So why would AI get you 6 dB? I mean, 6 dB is a very large number. In my group, our motto is you kill your grandmother for 2 dB. So you divorce your wife for 3 dB. But 6 dB is a very large number. I mean, why would AI give you 6 dB and excellent engineers not give you 6 dB? It's like, I mean, it's just a little bit unintuitive to me, this 6 dB number.
Well, yeah.
I mean, it's an affront to Professor Peter Asbeck with linearization. I mean, are you telling me that you can replace Professor Asbeck by an AI engine and get 6 dB more?
I'm not a magician, and I'm happy my wife is probably not watching this right now. So, that's a very good point. I'm not trying to get power out of thin air. Here, the power is already there. That's a key point. The 6 dB is already there. We're just not using them today because we are backing them off. So I'm just saying that if we allow us to operate in the nonlinear region, which we are not doing today, because of the obvious reason of impairments, then use AI to capture this, to figure out how to deal with these impairments, the clipping. That's how we were able to do that.
But can't we figure out the standard techniques of linearization, deep linearization into the compression region and to deal with it? And then compare our standard techniques of going deep into the into the saturation versus the AI and compare if there is a half a dB difference or 1 dB difference. And at that point, we don't kill grandmother and we don't divorce wives, basically.
Yeah. I mean, definitely. I think there's different ways of solving this problem. In the end of the day, maybe a combination of both. So if there's good ideas for linearization, definitely we should look into that as well.
Thank you.
Thanks.